All right, let's get another video. This time about, I guess this will be over Newton's second law. So let's take a look at Newton's second law. And this video, I think, to be efficient, what we'll also do is probably go over Newton's third and Newton's first. Why not, right? We start with the second. It's kind of weird. You're like, why not start with the first? I suppose we could, right? But generally speaking, when you work with this, you're starting with force and then kind of you learn what a force is, and then you can start learning about things like what inertia is and what equal and opposite is. But I guess that's an opinion, I suppose. If I could resurrect Sir Isaac Newton and ask him, maybe he could tell me, do momentum first. I mean, I could see that too. I've kind of thought about that before. But anyway, how do you fit this back into force, right? You're saying, what do you mean? Well, the slide before is about acceleration, right? So how do you fit acceleration back in? And you say, hey, F equals ma. That's Newton's second law. And then you say, well, A is in there, acceleration. And hey, F, probably for force. And then M, probably for mass, right? It's worth noting, just a little piece of information is a lot of people, misconception I see a lot, is people see M and they think, oh, it's probably meters, right? There's a difference between a unit, like the label we use for a unit, and then the variable that we use in an equation, okay? So like kg is a unit, right? Kilograms, okay? I suppose in an equation, if you had k times g, it could be some constant times the acceleration due to gravity, right? That would be weird though, okay? What I'm trying to get at here is just be careful. You see an m, you got to look at the context. Is it in an equation? Okay, then it's going to be mass. If it's like 16m, then it probably means 16 meters. So just a little thing, and maybe you're like, yeah, that's obvious, but sometimes it's not. Sometimes you might say, hey, I'm new to this. I don't know, right? And then it isn't obvious, but hopefully now it becomes more obvious or easier to work with, okay? So just something to keep in mind, okay? If we are looking for force, if we're looking for mass, if we're looking for acceleration, this equation lets us do it, right? Essentially, if I have two of these things, whether it's force and mass, mass and acceleration, right, any combination thereof, I can find the other one using algebra, okay? So there's ways we can work this, of course. All right, so let's keep on moving, okay? If I said calculate the force of a 16 kilogram object accelerating east at 4.55 meters per second squared. These are the easiest ones. All you got to do is plug your numbers in. 16 kilograms times 4.55 meters per second squared. Okay, easy because you don't have to do any really crazy math, right? You're just punching numbers in a calculator, basically. Notice the unit is newtons. Technically the unit. You might say, wait a second, where's the n coming from? That is a way to make it easier to talk about and easier to work with. All right. If you're like, well, where does it come from? It's kind of like, saying 12 is a dozen. It's easier to say a dozen than it is to say, well, I guess it's not that easier to say 12, right? But if I had 10 dozen, that's 120, right? And I suppose what I'm trying to get at here is that we might use units like this to make easier to converse about. It's just easier to say newtons than it is to say kilogram meter per second squared. That's a mouthful, okay? So we said, hey, let's just make that unit, let's call it newtons, with the understanding that it still is kilograms times meters per second squared. Okay, so just keep that in mind, all right? Some examples, right? So we have, I'm not going to read the whole problem to save time. But we have this steel ball. It's falling towards Earth. The acceleration due to gravity is negative 9.81 meters per second. Notice it's negative because it's going down. Okay, and I want to know how much force. This problem could jam you up because it's in grams, and this equation requires kilograms. So your first thing you got to do, of course, is convert the grams to kilograms. Essential, have to. Okay, if you don't, your answer is going to be wrong by 1,000. Like, as in you'll be off by 1,000 times, and that's quite a substantial error to make. So make sure the units are correct. Okay, so we convert the grams to kilograms, and then I can plug it in F equals ma. I'm doing it all in one fence post thing to show you that this fence post thing is basically doing the math in a more visual way. Okay, numerators, denominators being included. Okay, do you have to do it this way? No, but I think it might make it easier. Okay, so units canceling. And then we have kilograms times meters per second squared, which gives us newtons, okay? Harder problem, what if I had a ship? The mass is, 1.5 times 10 to the sixth. And I want to know how much force should the engine be able to provide to basically get this ship to a certain acceleration. Okay. And these are like, I mean, I'm not a ship designer, but I mean, these are like serious things you might have to consider if you're designing something, right? Like you make a ship bigger and bigger and bigger, it's going to need a bigger engine. And you might need to know, well, how much force the engine have to put out, right? If we put this on this boat, on this ship, will it be able to do the job correctly? And as you can imagine, there's more than just how powerful the engine is, right? There's more things you have to consider, okay? But I'm just giving you a general idea here, right? Something you might apply this to, okay? So I plug my numbers in. I have kilograms. I have meters per second squared. And I just multiply them across. Okay, so my mass times my acceleration is going to give me how much force, in this case, the engine needs. 3.03 times 10 to the 6th, so about 3 million newtons. That's pretty decent. Okay, but it's a ship, so it kind of makes sense. What else? An object is pushed, right? Again, you can always pause these and work on these, right? This is a video for you, obviously. You can always pause it. That's what's nice about a video. Right, we're pushing an object 105 newtons, and now I want to know how much mass. So now you got to rearrange your equation, right? Now you need to do some algebra. Okay, I have my force, I don't have my mass, but I do have my acceleration. So then what can I do? Divide by acceleration, right? Take my force and divide it. So I'm just showing you the algebra here, right? You're allowed to do this. If you're like, wait, how? How does that work? Well, I'm trying to isolate a variable. I want m by itself, okay? M should be by itself. Because I'm trying to find it. Okay, so I just rearrange the equation. If you need help with algebra, that is not that I'm saying I can't do that. It's just that this video is not about the basics of algebra. So if you need help, ask me or your teacher, right? Okay, so we do this math, yay, and what does that look like? I rewrote it for you just to make it a little bit easier to see. When you divide by a fraction, it can be scary. It's the same thing as multiplying by the reciprocal. Okay, I think that's an easier way to picture it. So what's your answer in this case? 9.5 kilograms. Okay. I even also wrote out here the full unit for force, right? It doesn't say newtons. It is newtons, but I wrote it out as its full form, kilogram meters per second squared. So you can see, what cancels out, of course, and what we're left with, right? Just kilograms. Hey, it's almost like this math thing is useful, okay? So as I promised this video, I would get into the other laws of motion, so we'll do those quickly. Okay, they're not, I'm not saying they don't matter. I'm just saying there's not a lot of calculations to do with them, okay? So, ironically, as I say here, Newton's second law, everyone always forgets it, which is a shame because it's probably the most important one. However, we have the other two, Newton's first and Newton's third, okay? So Newton's first law of motion is an object in motion stays in motion unless acted on by an outside force, or I say here external, same thing. All that means is that something that's moving will keep moving unless something gets in its way or is creating a force, or is a force is acting upon it to slow it down, to cause it to accelerate backwards, which is a fancy way of saying slowing down, right? Or if it gets faster, right? I suppose that would also work, except that's not usually how we think of it this way, okay? If an object's at rest is a velocity of 0, you need force to cause it to accelerate, right? So you need a force acting on it for it to accelerate, okay? When we say external force, it's because you can have what are called internal forces, okay? And this gets kind of messy. If you're taking a physics class, you'll definitely learn about what are called systems, okay? Like a system is like, imagine like a way of thinking of something and what's happening inside and what's happening outside, okay? So like if I ate an ice cube, right, I'm introducing that into my system, literally and figuratively. That will cool me down, right? Because I'm eating something that has lower energy and my body has higher energy, which will cause my, think of it as like my average energy to decrease, which makes me feel cold, right? Decreases my energy, okay? That's a systems problem, okay? I don't want to go too far into this. This is a video for another time. But basically, external means outside, something on the outside. So friction, right? If I'm moving across a table, right? Yes, I keep moving, but what's going to slow me down? The friction of my arm in this case, or I said table. I don't know why I said table, but whatever, right? That'll slow me down, okay? That's an external force, okay? If I'm falling through the air You say, gravity's pulling me down. It is, right? And you might say, shouldn't I keep getting faster and faster? You do, until the resistance of the air resistance, is pushing up enough that I can't get any faster. Okay? So I've reached what's called terminal velocity, which is a fancy way of saying I'm in trouble if I hit the ground. Well, even before that, I'm probably in trouble. But the point is, terminal velocity is the fastest something can fall on Earth. And guess what? It depends on mainly how big the object is. And by big, I don't mean mass. I mean like how much surface area it has. So a parachute, right? What does that do to your terminal velocity? It lowers it. And that's why we use parachutes, right? I use a parachute because I don't want to hit the ground too fast. If I do, the acceleration will kill me. And when you say acceleration, what do you mean? Well, if I'm going 100 meters per second down and I hit the ground, guess what happens to me? All that velocity within maybe half a second, quarter of a second, maybe a second and a half, depending on what surface I hit, my velocity is zero. That's a force, right? And that's what would would be my undoing if I hit the ground, right? Okay. So anyway, going off on a tangent, but hopefully it's interesting. All right, and again, I kind of just described this. You basically describe this as a force. Hey, exactly, right? A force is what causes that. Okay. This law describes what's called inertia. Inertia is the concept that objects will keep moving until something stops them. Okay. Momentum, right? A little bit different, but momentum is, and we'll get into this when we get to energy. This concept that something is moving and it wants to keep moving, and if I want to stop it, it's going to take some energy to stop it. Okay. Remember, forces, to apply a force, you would need some energy. Okay. So these things are very related. And I mention this not to confuse you, but to show you that there's a lot of things in science that build off each other and are similar. And it's important you know what these words mean. All right. You don't just throw them around and say whatever, right? You have some understanding of them. Okay. And again, we talked about this idea. I gave this example. Yay, yay, yay. Okay. That's Newton's first law. Very simple, very logical, very intuitive. Okay, I think you'd agree. Newton's third law is not intuitive, not very simple. Okay, so I would definitely think the first law is the easiest. The second law, I think, is probably second easiest. And the third law is by far the hardest one to understand. You may have heard of it before. I bet you probably have this idea that for any force acting upon an object, there is going to be an equal and opposite reaction. Okay? And this sounds nice. You're like, oh, I've heard that. But what does it mean? It means weird things. It means that, like, if I jump, how do I jump? Well, with my legs, I don't have 3 legs, I have 2 legs. I bend my knees like this, and then what do? Think about this. When you jump, you are pushing down, and that causes you to go up. You don't grab your shoulders and pull yourself up, right? You don't do that. You bend your knees down like this, and you have like a spring with your legs, basically, and then you very suddenly push down. Okay? What's happening? You are pushing down on Earth, and this is the part you're not going to like. The Earth pushes back up on you. The Earth says, no, you, and makes you go up. Okay? That's how that works. If you're a swimmer, or anybody who's ever swam, I don't know which one is. English is weird. You go to the wall, right? Swimming, here's the wall, and what do? You do a flip, and then your legs are against the wall, and what do you do with your legs? Hey, kind of like pushing off the ground, jumping. You bend your legs and then push, okay? Same thing here. You're pushing against the wall, and the wall is pushing back against you. That's what moves you forward, okay? It's not very intuitive. You're like, how is it doing it? It doesn't have arms. It doesn't. It's the fact that you're pushing into it. It responds by pushing back against you. Okay. This is how rockets work. How does a rocket work? It's shooting hot gas out of the back of it, out of the bottom of it, and that makes the rocket go up. Okay. So just some examples here. Hopefully you're going, okay, kind of get you. Okay. You should be thinking of this as direction. Force is a vector. I go this way. The response force is the opposite. There we go. Geez, the opposite way. Okay, vectors. All right. Hopefully you're saying, kind of get it. Okay. And we often say action, reaction, right? So I gave you the example of the rocket. The rocket is pushing down on the Earth, right? And the Earth, well, it's a little more complicated saying the Earth. The air, the Earth, etc., are pushing back up, which causes the rocket to go up, okay? A cannon or a gun or whatever, you fire it, and what happens? It goes backwards because of recoil. You say that's recoil. Recoil is because of Newton's third law. Okay. If you were in outer space and you took a bowling ball and you threw it in front of you, guess what would happen? You would propel yourself backwards. Okay. Yeah, it's something that's not super intuitive, but it's there. You can demonstrate it day after day. The way we walk, right? How do you walk? You're walking on the ground like this. I guess I'm walking backwards. How does it work? You put your foot down, and then what do? You are pushing backwards if you think about it, right? Next time you walk, think about this. Your foot hits the ground, and what do? You're basically pulling backwards, which propels your body forwards. Okay, it's kind of odd, right? But that's Newton's third law for you, okay? So hopefully that's making sense. And applying it just means, think about the math here. If I apply 600 newtons of force down, the Earth applies 600 newtons of force up, okay? And again, we can all take that very useful, right? Again, if you're a rocket scientist, if you're designing something, tires, right? A tire hits the ground and pushes this way, which moves the car that way. Okay, so just thinking about these things. It's not made up, I swear. You can check it yourself, okay? So I guess I got this last problem. I think we'll finish the video with this problem. 1,000 kilogram rocket, 3,000 newtons of force, by its engine for 20 seconds. How much velocity after 20 seconds? So we got to do what? We got to figure out force, and then we can use that to find acceleration. And then we can use that, or I'm sorry, we have force. We have force. So we're going to find acceleration. Apologies. We can find acceleration. If I find acceleration and I have time, I can find velocity. Okay, and if we had some calculus, we can find displacement as well, but that's above the scope of this video at the very least. Okay, I have some videos I'll probably have about that. Check those out if you're interested. Okay, I like to plan things out, especially if you're new to this. It's a good idea. You say, what equations am I going to need? I have force, I have mass, I probably need F equals ma, right? Think about, a toolbox. You see a nail, you reach for a hammer, right? Because you know the hammer's for nails, right? You know force. You think Newton's second law. That's a good thing to think of, okay? So then I list out my variables, 3,000 newtons, 1,000 kilograms. I can find acceleration. And then I say I'm trying to find velocity. And if I have acceleration and I have time, I can easily find that, okay? Assuming it's constant. But that's another conversation. So I can take my acceleration, which I believe we said was, I guess I don't have the slide for this, which is kind of, oh, it's right there. Okay, just the order. When I made it in PowerPoint, I guess I didn't put it in the right order. Shame on me. So up here, we're solving for A, right? So 3,000 divided by 1,000. Hey, that's nice. That's 3 meters per second squared. And then I can say I have 15 seconds. You can see the units cancel out, and you say 45 meters per second, okay? So we'll call it quits here for this video. I hope you have a great rest of your day. And again, if you have any questions, please put them in the comments. Awesome. Have a great rest of your day.